My name is Holden Mays, and this is my video lab report for Lab 1 for Physics 2212 at Georgia Tech. This video will cover the lab in 6 sections, beginning with an introduction to the lab, followed by assumptions made during the lab, the measurements acquired during the lab, a computational model that helps visualize information, calculations made using the measurements acquired, and lastly, 2 discussion questions. The goal of this lab was to find the approximate charge of a piece of tape after being rapidly torn apart from an identical piece of tape using Coulomb's law and Newton's second law of physics. When two pieces of tape are rapidly pulled apart from one another, one piece of tape rips electrons from the other, resulting in two pieces of tape with opposite charges of equal magnitude, one positive and one negative. By repeating this, multiple pieces of tape of the same sign with approximately equal magnitudes can be acquired, which will repel each other. When two like-charged pieces of tape are placed atop one another, the repulsion between the two pieces will cause one to float a certain distance above the other. This distance can be used with Coulomb's law to calculate the approximate charge of a piece of tape. The tape used in this experiment was found to have a negative charge as it was repelled by a pen with a no negative charge. Coulomb's law states that the electromagnetic force between two charged particles is equal to the product of the two charges multiplied by Coulomb's constant and divided by the distance between them squared. When one piece of tape is floating, that electromagnetic force is equal in magnitude to the force due to gravity acting on the tape, which allows the charge of a piece of tape to be calculated. Several assumptions must be made in order to use Coulomb's law for this lab, however. We need to assume that the force due to gravity and the electromagnetic force are the only two forces acting on the floating tape in the vertical axis. We must also assume that each piece of tape acts as a point charge, and that the charges of the two pieces of tape are equal in magnitude. This experiment was performed with two pieces of tape that were 20 centimeters in length, 2 centimeters in width, and had a mass of 0.2 grams. Performing the experiment, one piece of tape floated 0.6 centimeters above the other one. A computational model was made in GlowScript to represent what was observed during the lab, visualize the forces acting on the floating piece of tape, and calculate the magnitude of the charge of the floating piece of tape. In the computational model, the floating piece of tape, labeled tape B, is represented by a blue point. Tape A, the tape used to make tape B float, is represented by a red point. The blue arrow pointing down from tape B represents the force due to gravity acting on tape B, while the red arrow pointing up represents the electromagnetic force acting on tape B. The two arrows representing the vertical forces acting on tape B are equal in magnitude, which indicates that there is zero net force acting on tape B in the vertical axis. Tape B's charge was calculated in GlowScript using Coulomb's law, rewritten as the magnitude of tape B's charge is equal to the square root of tape B's mass multiplied by gravity multiplied by the distance between tape A and tape B squared divided by Coulomb's constant, which is 9 times 10 to the 9th power. Tape B's charge was found to have a magnitude of 2.80143 times 10 to the negative 9 coulombs, and was found to have a negative charge through the previously mentioned experimentation. The number of excess electrons in tape B was also calculated in GlowScript by dividing tape B's charge by the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs. Tape B was found to have approximately 1.75089 times 10 to the 10th power excess electrons. Since tape B was 20 centimeters long and 2 centimeters wide, tape B has an area of 0.004 meters squared. If tape B's negatively charged adhesive side is treated as two-dimensional, then the number of atoms that make up tape B can be approximated by dividing tape B's area by the area of an atom, which is 1 times 10 to the negative 20 meters. Tape B consists of approximately 4 times 10 to the 17 atoms. Dividing the number of excess electrons by the number of atoms in tape B's adhesive side, tape B has one excess electron per approximately 22,845,524 atoms. This means that, when ripped from the starting piece of tape, tape B only stole an electron from 1 in 23 million atoms. If protons and electrons switched charge signs, there would be no changes made to the lab. The calculations used only found the magnitude of tape B's charge, and all observations made wouldn't change since like charges would still repel all the same. The switching of signs would be an arbitrary change. The tape used in this lab had to be handled as little as possible, since excess contact with the tape would facilitate the movement of electrons into or out of the tape. Contact with less negative materials would allow electrons to flow out of the tape, lowering the magnitude of its charge.